recording this. Right. By the way, there is one thing actually I would like to just share with you. So the last time I remember that the Sajini asked the question about this dark matter, and she has also sent a link to me that where she found that. In fact, I haven't seen that as well, though I know about this particular survey, and there was a so I searched it a little bit more, and so I guess it's more appropriate. It's actually more appropriate for us to discuss about that as well. And I think I have shared this particular YouTube video with you, and I'm not going to share it again. And I hope all of you can see watch it. And the idea is there was also this article. Let me take that as well. Actually, sorry about it. I have actually prepared everything. Unfortunately, I had to restart the computer. Then I need to look at all these things from the beginning. In fact, this is I guess you can see this article. This is the article that she sent to me, the new dark matter. So it's kind of interesting that they are allowed to use now for some reason. Anyway, so what I can actually share that article as well. What that article mentioned is that there is a survey that goes on for now for a few years called Dark Energy Survey. The idea is they try to map the dark matter in the universe, right? And once they map the dark matter in the universe, they found something very interesting, that is the distribution of dark matter that they have seen is more smoother than they expected from Einstein's general theory of relativity. The general theory of relativity is the main theory that we use to measure this gravitational effect. And dark matter is, even though you cannot see it, it is the effect of the dark matter you can observe, right? The way that they do it is, now when you have this dark matter, you can measure that effect somehow, right? So I'm not going to go into details, but so what they have found is the dark matter is more smoother than they expected, because there were some previous research, like the models, computer models that the astronomers have created according to the general theory of relativity, and they predict how the dark matter should be distributed. But so the idea is, normally we expect that more dark matter will be distributed close to the galaxies, especially in the halo part of the galaxy. If you remember the topic about the galaxies, we have discussed about it. But what they have found was something very interesting from this dark energy survey, is that this matter is more smoothly distributed than they expect, right? So this should be a challenge in future for the general theory of relativity, because this kind of deviates from the general theory of relativity that we are learning. Even though we didn't talk about the distribution of dark matter and everything, you can predict those if needed. And so that's the story that she has shared. The one thing actually I didn't understand was what Sajini exactly need to know. But so one thing that I was wondering is, there was a map that they don't. I think I can share it now. So this is that article, and this is the telescope that they have used for this the dark energy survey. That they found all this information, and this is uh, the 4-meter telescope, which is in, I guess, in Chile, in South America. And I know this telescope because we had a time that we took some data using this telescope as well. So I haven't been to here due to some reasons with the restrictions that we had at that time. But so I have taken data, and one of your former special degree student called Lakmal, he is working closely with this telescope with the data, and I know that they have continued this survey at that time as well, the dark energy survey. And so I'm not sure whether Sajini is asking why you have only part right here mapped from this survey. Like you can see that there is only this the purple area that you can see is the area that they have data for the dark energy. And I was assuming that Sajini's question may be why we have the data, or why the dark energy is distributed only this area. If this is the question, Sajini, the answer is actually this is the area that they have surveyed only from this telescope, right? Because this particular telescope is in the southern hemisphere, so it can only see the south part of the sky. And again, there is a limit that you can rotate the telescope, right? You can just look at things in the horizon, and there are this kind of problem. So that may be the reason that they have only this particular region scanned through the telescope for to map the dark matter, right? So I guess if that is your question, then this will be the answer, right? So if it is not your question, then let me know. I can then figure out what actually you asking, right? So that is the that is what I want to tell you about this article. And so let me go back to our original thing. Right, so the last time we have discussed about the cosmological principle, so not cosmological principle, these observations. So we have discussed about the cosmological principle, which tells us that basically the universe is isotropic and homogeneous. And at the same time, the next thing that we discussed is the evidences. So we talked about large galactic surveys, and then the quasar survey, which is also related to the same 2DF survey, and then observations of the cosmic microwave background as an evidence to tell that the universe is isotropic and homogeneous, right? So these are the three evidences that we have discussed. And today I'm going to start from this cosmic microwave background because right, so let me start with the cosmic microwave background, because this is also important as a very strong evidence for the Big Bang theory, which is the theory that we discuss and currently acceptable theory for the beginning of the universe, right? And the idea is this cosmic microwave background radiation, or CMBR, is a faint diffuse glow coming from all directions of the sky. Now, if you go outside and measure it, you should be able to measure this cosmic microwave background radiation that comes from each and every direction of the sky, right? And however, the first time this is discovered is only in 1965 by two astronomers called, not actually astronomers, one was an astronomer as far as I remember, and they discovered this in 1965 accidentally, and for this discovery they won the Nobel Prize for their effort. Now, when you do a spectral analysis of this cosmic microwave background, what that shows is that uh, this background radiation perfectly fit to the black body spectrum, right? And I hope you remember the black body spectrum curve, right? For example, we normally assume that our sun is a black body and there is a spectrum, right? How the wavelength, change, how the intensity of the wavelength change. And what they have found is that this is a perfect fit to the black body spectrum with the temperature of 2.75 Kelvin. Now, you know that when you say it's a black body spectrum, that can have different temperatures, right? The temperature of the sun is different. Like that, for this cosmic microwave background, it's a perfect fit to the black body spectrum. So it shows the black body spectrum, and the temperature of that is 2.75 Kelvin. You can see that it's very cool compared to uh, the other spectrum, such as sun. And this graph basically shows you what has happened over the years to this cosmic microwave background radiation. And I would like to talk that with the information that I have below. This, as I told you, this cosmic microwave background radiation is also considered as an excellent evidence for the Big Bang theory. Basically, what the Big Bang theory predicts is that uh, there is a hot, dense universe with highly energized subatomic particles, right? And you wondering what are subatomic particles? Now, subatomic particles are things like quarks and leptons. And I'm not going to talk too much about that because you will have a separate course about particle physics and nuclear physics. And so what has happened was initially there was a hot dense state for the universe with all these highly energized subatomic particles. Then the universe started to expand from that particular point, right? So once the universe get expanded, at the same time it get cooled down, right, for several hundred years, and then the temperature of the universe has reached to a temperature of 3000 Kelvin. Right? So that is what has happened from the initial point of the Big Bang. Initially, there was a hot, dense universe that we had, and then uh, it started to expand. And once the universe get expanded, universe also get cooled down at the same time. And after several hundred years, the temperature has reached to 3000 Kelvin, right? So this is what has happened during the Big Bang. And then this expansion of the universe redshifted this radiation to current temperature of 2.75 Kelvin. Once the things get expanded, they get redshifted, right? And we will talk about that in next section as well. Once they get redshifted, then you have this current temperature of 2.75 Kelvin for the cosmic microwave background, right? Now, according to the Big Bang theory, we believe that this cosmic microwave background radiation has emitted about 13.7 billion years ago, right? And this is pretty much close to the age of the universe, not exact, right? The age of the universe is a little bit more than this, right? And as to support it, I have mentioned here this time is around 400,000 years after the Big Bang. So once the Big Bang happens, that is the uh, that is the t equals 0 event. So that is where we started to measure the time. Right after 400,000 years, after the Big Bang, then the universe get expanded and cooled down. And then you have this cosmic microwave background radiation at that particular point, right? Now, the Big Bang theory nicely explains each of these steps, which I'm not going to explain here. But once you have this reading assignment, you can get a nice idea by combining all these things. right? And now let's move on to this graph right here. And this basically explains what has happened to this cosmic microwave background radiation due to the expansion of the universe, and hence due to this redshift, right? And initially, right, this cosmic microwave background radiation curve was something like this, right? It has peaked around here, which is, correspond to gamma rays wavelength. And after 10 to the power 5 years, it has gone to optical wavelength. And after 10 to the power 7 years, it has gone to infrared. So this is how it is, redshift with the time. And today it is seen as a radio wavelength. And at the same time, the peak intensity has gone down as well, and it has cooled down. So that is why the something that was, had a temperature of 3000 Kelvin at that time, but once you see it now, it is highly redshifted, and the temperature has gone down to 2.75 Kelvin. And because of that, when you observe it now, we are seeing it in radio waves. So that's why we used to call that cosmic, not radio waves, sorry, it should be microwaves, right? Cosmic microwave background radiation. Right, so that's a brief, a brief story about the cosmic microwave background radiation. And so that now let's look at a little bit more details about this redshift, right? Now, I think we have talked about the Hubble's law previously as well, but it will come again and again because it is connected, especially with the cosmology part. And if you remember the different types of redshifts that we have talked up to now, we have basically talked about two types of redshifts. The first one is called the Doppler redshift, and the second one is the gravitational redshift that we have talked during this course, right? And I hope everybody knows what Doppler redshift means. Doppler redshift means when something is moving away from you, and you have, studied about this even in your A-level physics, that, in terms of the sound, right? When the sound is moving away from you, the frequency that you hear will be less, right? When something comes to you, it will increase like that. If something is moving away from you, the wavelength will be redshift. Right? So that happens due to the relative motion of two objects, and that is called Doppler redshift. And everybody knows about that. And then we learned about this gravitational redshift very recently, like a few weeks ago, as a consequence of the curvature of the space-time close to a black hole. Right? So that is the second type of redshift that we have learned. And there is a third type of redshift that we are going to learn now, and that is called cosmological redshift. Right? Now, this cosmological redshift is actually directly related to the Hubble's law, because this particular redshift happens due to the expansion of the space itself. Right? So remember that these three redshifts are three different types, right? Gravitational redshift, Doppler redshift, and cosmological redshift. Right? So the cosmological redshift is basically due to the expansion of the universe, so the expansion of the space itself, which is a completely new one for us. Now, normally we use this particular equation to calculate the amount of redshift. So that is Z equal lambda observed minus lambda emitted divided by lambda emitted. Right? So what that means is you will get the observed wavelength, and then you know the emitted wavelength, and you take the difference and take the ratio, and that is what we define as the redshift. And as you can see from the equation, the redshift values do not have a specific unit. It is just a number, and something that is so far away will be highly redshifted because the observed and emitted wavelengths will have a larger difference, right? So that's how it works. And even sometimes this value of C can be less than 0. And if that is the case, then we used to tell that it is blue shifted. So that the idea is observed wavelength is smaller compared to the emitted wavelength, so that you will get a negative value here. So if the observed wavelength is smaller, so what that means is that particular object is coming towards you, right? So instead of red shifted, it should be blue shifted. So if that is the case, this value Z should be less than 0. So that's what I have mentioned here. And for the red shift, it's obvious that it should be greater than 0, right? Now, this the values of the red shift and the velocity of the receding object also related to each other. So that's why these redshift values are important for us. And if the redshift values are smaller, specifically if they are less than 0.1, then the velocity of a receding object can be given as V equals C times Z, right? And this is how the redshift and the receding velocity is connected to each other. And this is what exactly Hubble used to derive this experimental law called Hubble's law, right? Because if you remember, we have talked about the Hubble law before as well. And if I go down a little bit, this is the plot that he had for the Hubble's law. So what he had measured was precessional velocity. So that is the velocity of a galaxy that is moving away from us and the distance to that particular galaxy, right? So then what you can see that what Hubble had to do was he had to select a large number of galaxies, and for each galaxy he had to measure the distance and then the recessional velocity, right? Now see that all the knowledge that you have acquired in this course can be used to understand something like this. Now, to measure the distances for these each galaxies, what he had used at that time was these Cepheid variables. Remember that we talked about Cepheid variables at the beginning of the galaxies, right? Cepheid variables are, one of the methods that we use to measure distances to galaxies, right? Because the Cepheid variable means it's a type of variable star that will lead to this period luminosity relationship, and we use that to measure the distances, right? And just go back and look at that section. It nicely explained how to measure the distances to these nearby galaxies, especially for the nearby galaxies, right? Because when the galaxies are so far away, it's hard to identify individual stars. So that this works nicely for nearby galaxies only. And the other thing is precessional velocity. Even though we talked how to measure the distance at that time, we didn't talk very deeply how to measure this recessional velocity. So he had measured the recessional velocity in this way. So first he found a galaxy and he obtained a spectrum of that galaxy. And once he obtained the spectrum, the advantage is he can actually take few of these emission lines, and then look at how they are shifted than expected. Right? For example, let's say you are looking at the hydrogen line, and you know that, for example, if you take the H alpha line as an example, H alpha has a specific wavelength. So that is 6563 line. That's how we call it. So that is 6563 angstroms, right? So that is the wavelength. And once you observed it, if it is shifted, let's say for a higher value, then you can observe the shifted value and take the difference with the emission value and divide by lambda emission value and take the redshift value, right? So that's how you calculate the redshift. And once you calculate the redshift, you can use this equation right here. V equals z times c, because the c is the velocity of light, to find the recessional velocity. So that's what Hubble did exactly to make this plot, right? And at that time, we didn't have the technology to, measure the distances to galaxies that are so far away. So he only considered the nearby galaxies. And because of that, these redshift values are less than 0.1, right? And it should be because they are very nearby galaxies. Because if you are going to measure the galaxies, the redshift values that are greater than 0.1, then you have to modify this equation to a different form. So that's why it has specifically mentioned that this works only for the redshift less than 0.1, right? And right now, so Edwin Hubble used this relationship to find the recessional velocity. So that's what I have discussed with you for a sample of galaxies. And he measured the distances to sample of galaxies. And I have mentioned here, look at the PHY4224 nodes for more details, because I have explained all these things there as well. And once he measured, he had this graph. And as you do in practicals, Hubble did the same thing. Okay, the points looks like, it's in a straight line. So he made the best fitted line here. And the only difference here is in your practicals, in physics practical, that you know that it should be a straight line, and you may derive the theory and then make a straight line, and then you check it whether it's correct or not. But in this particular situation in 1929, Hubble did not know anything about, these relations or anything like that, and there was no theory about it as well. And what he did was he, looking at distances and recessional velocities and plot all these data points. And then he realized that, okay, when you increase the distance, the recessional velocity is also increasing, right? And then he plot all these data points on a graph. He see this nice linear relationship, and there are, some points that are off by little amount, but you can very clearly fit a line for that. And that's how this Hubble law came into play. And then he derived the velocity equal h naught times d, and as you can see, h naught is the gradient of this graph, and it is a constant, and that's how he defined the Hubble constant at that time, right? Now, so one of the fundamental features of this Hubble law is that it clearly explains the expanding universe, right? Because galaxies that are far away from us, moving away from us, according to this graph, right? Every galaxy is moving away from us, not only single one or two, right? Now, this large scale motion of all these galaxies are actually due to the expansion of the universe. And we have a specific name for that. So that is called Hubble flow, right? All these galaxies are moving away from us due to the expansion of the universe, not due to anything else, right? Now, the reason why we think about it in that way is that we know fundamentally all the galaxies, it has matter, and then there is dark matter that also gives you the influence of the gravity, right? Which means attractive forces. So that means we, in general, we normally expect that all these galaxies should come towards us, right? So don't you think it in that way? So that's what I feel, because, all these galaxies are huge masses, and they have a very huge gravitational effects, and gravity is always an attractive force. So what we normally expect is, if you think about the relative motion of two galaxies, these galaxies should come towards us, right? But what Hubble is explaining here is all galaxies are moving away from us, right? So these two, contradict if you think about it, right? I mean, if you don't think about it, you don't have a problem, but I think you should. And you have this question, right? Because when I was learning about this, I had the same type of questions. How these galaxies are moving away from us, and they are coming towards us. Actually, there is one galaxy that is blue shifted, which means coming towards us. Anybody knows what is that galaxy? It's one galaxy. So I may have mentioned it earlier as well. Who knows which galaxy is coming towards us or blue shifted? Nobody knows. What is the closest galaxy for us? Closest larger galaxy for us, large galaxy for us.
So is it Andromeda
One is
galaxy?
closest to us.
So is it Andromeda galaxy?
It's surprising. I guess we should. Yeah, that's correct. That should be Andromeda. So Andromeda galaxy is the closest galaxy for us, and this is the galaxy. In fact, you can see a blue shift, not a red shift. If you look at the spectra, right? Which is interesting, and you can. The reason should be obvious because uh, the gravitational effect is dominating there because it's very close to us, and because of that, it has a larger attractive force, and uh, it's since it is close to us, its recessional velocity should be smaller as well, right? According to the Hubble law, the closest one have a smaller recessional velocity, which is moving the velocity that is moving away from us, which means this galaxy, if you combine the effect of the Doppler redshift and the cosmological redshift, the Doppler redshift dominates there, right? So that's what has happened, even though it is expanding, right? Almost all the other galaxies are actually redshifted, moving away from us, and that redshift is due to the expansion of the universe, and because of that, we call that particular redshift as the cosmological redshift, right? So remember, these are different terms that you use, right? There are some more information for at any given time Hubble flow. So as I told you, overall large scale motion of galaxies is due to the expansion of the universe, and that is known as the Hubble flow. And at any given time, Hubble flow can be described as a single rate of expansion. And as you can see, that rate of expansion is the gradient of this above graph, which we called as the Hubble constant, right? Now, it is interesting to look at how this expansion actually works, right? Because something that most of the time students get confused, because we talked about different redshifts here, and when you look at this expansion of the universe, it is important to understand what actually happens here, right? Now, for that, I have a small diagram here. So if you haven't seen this before, this is what actually happens, and you can see that there are two observers. Observer A is right here, and observer B is right here. And let's say this is our universe, and this get expanded. So you can see that when you get expanded, all these dots are moving away from each other, right? Now, so I have mentioned it here. Consider a dots painted on a spherical balloon. Think about this as a spherical balloon. You can actually, if you have a balloon, you can check this as well yourself. And so there are dots painted on the balloon. And then once you, let's say once you expand the balloon, these dots will separate at a rate proportional to their distance apart, right? So because uh, the the two dots that are so far away will uh, expand in more higher rate, compared to the two dots that are close by. So that's what this particular diagram explains. And the other thing is, if you look at this observer A and observer B right here, they were here and here in the smaller balloon before it get expanded. The observer A on a particular dot will see that all the other dots moving away from him and might feel that he is at the center, right? Now, let's say you are the observer A and you are in this earth, and then you feel that all the other dots surrounding you are moving away from you, and this give you a false sense that you are at the center, right? So that's what you normally feel now. If when you feel that everything is moving away from you, you feel that you are at the center, right? However, if you look at the observer B, uh, who is in a different location, he will also feel the same thing, right? All the other dots that is surrounding him will also move away from uh, him, right? So he thinks that he is at the same time, right? Now, that what that means is there is no center from which everything started to expand, right? So there is no particular center that you can tell that okay, from this point everything get expanded like that, right? So you cannot uh, call it in that way, right? Now this idea has a specific name that we call as Copernican principle, which tells us that there is no central privileged location in the universe, right? So there is no, very privileged location in the universe. There are no locations like that, right? Now in Earth, that we have, if you compare it with, our day-to-day life, we have, certain privileged persons that get certain specific facilities compared to the others like that, right? So they feel that they are kind of in the central part that get more privileged things, but the universe in the cosmological scale doesn't work in that way, right? So there is no central privileged location in the universe, so everything is same. Now, as I have mentioned here, mentioned above, the motion of galaxies also affected by the gravitational effects from other galaxies, right? And this component, which is not explained by the Hubble law, is referred as the peculiar motion. So that means we only talk here the galaxies are moving away from us due to the expansion of the universe, and I explained how that expansion actually works. However, galaxies are also affected by these gravitational effects from other galaxies. Right? So that gravitational effects will give you, attraction forces, and that is not considered for this Hubble law. And that particular component, which is the motion of galaxies due to the gravitational effect, has a specific name called peculiar motion, right? Right. So I guess you probably have get a good idea about Hubble's law and how it is connected with the expansion of the universe and what actually this expansion means, right? So I want all of you to understand these three things. And so that is very important that you get the idea what this expansion means actually, right? It is not that you are right here and all the galaxies are moving from us. It is actually not the galaxy actually moving away from us. It is the space that get expanded, and all these galaxies are in the space now. So once the space get expanded, all the galaxies, they move away from each other. So that's what happens in this expansion of the universe, right? So I guess this will clear up some of your problems that you may have. And before I go into the next section, anybody else have any type of questions up here? Right. So if you do not have questions, let me move into the next section. Now, up to now, remember we have talked about the homogeneous and isotropic universe, and we discussed some of the evidence that we have as observational evidence to tell that universe is homogeneous and isotropic. And this cosmological principle is the basic principle that we need to understand when we talk about the universe. And then we talked about, a little bit more about the cosmic microwave background, because it is not only related to, not only considered as an evidence for the cosmological principle, and at the same time it is a very strong evidence for the Big Bang theory as well. And because of that, we discuss it a little bit more. And after that, we actually move into the Hubble's law that gives you another aspect about our universe. And we talked about the cosmological redshift and the expansion of universe based on the Hubble's law, right? So that's what we did. And now uh, we know that the universe is homogeneous and isotropic. Now we need to know a kind of a mathematical way of explaining this, right? Now, as you know, in Einstein's general theory of relativity, we discuss about the field equation, and solving field equation, actually we can get a lot of information, right, about our universe. And here what we need to, and in order to, solve the field equation, you should know the components of that. Basically, you have you need to have a metric. So once you solve a metric, you can get, connection coefficients and Riemann curvature tensor and Ricci tensor and Ricci scalar, right? Remember we talked about these things earlier. So that will complete the left-hand side of the field equation. And on the right-hand side, there is this energy momentum tensor. So you need to find out the energy, what kind of energy momentum tensor that explain the universe, right? So if you have those two components, what you can do is plug those values to the field equation and then solve the field equation, and it will come up with, set of differential equations that can explain the universe, right? So that this is what we are going to learn here. But remember very briefly, because due to the time limitations that we have, I am not going to go through, very detailed calculation. But at the same time, I want all of you to give you the idea, right? How you solve it, and from the results that we would have, what kind of things that we can discuss, right? And as the first step, the first thing is we have to define a metric that explains or describe the universe, which is both homogeneous and isotropic. Because from the observations, we know that our universe is homogeneous and isotropic. And because of that, we have to define a metric that satisfies this condition, right? So that's what we are going to do here. And in 1930s, there was an American cosmologist who called Howard Robertson, and a British mathematician called Arthur Walker. So they independently derived a specific metric, which we called as the Robertson-Walker metric, right? And that is considered as the most general possible metric that describe the space-time that match with the cosmological principle, right? Now, so let's start from that particular metric. So I'm not going to, go through how this metric is defined and all these things, but we will start from that metric. The most common form of that metric is written here, that is ds squared. So that basically gives you the line element. And then it's given as c squared dt squared minus r squared t. And then inside brackets, I have written here the spatial component. And this is some of the terms should be pretty, familiar with you. But there are certain terms that may not be familiar, especially these two terms, the K and R are very important here, which are two new terms that explains, the curvature and the expansion of the universe basically. And RT right here is called as the scaling factor, and this K is called the curvature parameter. We basically define the curvature from that value. Right, so let's look at some of the terms here in the Robertson-Walker metric. And this T is known as the cosmic time here. And then this time is actually is the time measured by an observer whose peculiar motion is negligible. And you know what is peculiar motion, right? I have introduced that word previously. Peculiar motion is the motion due to this local gravitational effects, right? So if you consider that as a negligible effect, then you get the motion due to the expansion of the universe, and this time is measured by an observer who is, in this, when you neglect this peculiar motion. And what that means is actually the expansion or the contraction you get is due to the homogeneous and isotropic space-time. Right? Now, we know that our universe is expanding, but we consider both situations here. The both expansion and contraction is due to the homogeneous or isotropic space-time. Right? And then with this time is called cosmic time, if that is the case. And remember that the peculiar motion is the one, if you consider that, contraction, that the peculiar motion, if you consider the peculiar motion, there should be a contraction due to the gravitational effects, but you normally ignore it in this particular point, and we only consider the expansion or the contraction that happens due to the homogeneous and isotropic of space-time. Then this time is called the cosmic time, right? And then we have a new word right here. Observers who share the same cosmic time are called as fundamental observers. So they basically have the same cosmic time. And in expanding universe, fundamental observers are moving with the Hubble flow, right? So that means, Hubble flow is, I have explained it earlier. So that's you are actually, think about you. Actually, if you are in a galaxy, then let's say you are some of one another observing another galaxy. So both of you are actually moving with the Hubble flow, right? Because you are in this expanding space. So that kind of observers are actually fundamental observers if you are moving with the Hubble flow. Now, when you assign coordinates to these fundamental observers, those coordinates are called co-moving coordinates. So for example, in this Robertson-Walker metric, you have r, theta, and phi coordinates. And if these coordinates are assigned to a fundamental observer, then those coordinates are called as co-moving coordinates, right? So make sure that you go through this note again, because there are some new terms that we normally do not use in other subjects, right? Now these coordinates remain as a constant with time for any point. And I have a figure here just to show you what this co-moving coordinate means. Now, here are 3 points in a triangle in this lower diagram. And once with the increasing cosmic time, all these 3 points are expanded. You can see that this point right here is right here, and this one is here, and this one is here. And you can clearly see that all those 3 points are expanded once the cosmic time is increased, right? But all 3 of them are moving with Hubble flow, or they are co-moving coordinates. And you can see that as in this figure, coordinates describe the position of the triangle remains the same, although the grid has increased its size. So it is the grid that has increased the size, right? So these two coordinates, let's say you have XYZ here. So that XYZ will be there. And even if you go into this diagram, this will be XYZ. At the same time, the whole coordinate grid has expanded, right? So which means the positions will not change, right? So these coordinates will be the same, right? So that's what I want to tell. So just go through the note and try to understand it. And now then the other parameters that you see in this Robertson-Walker metric, now the K is called as the curvature parameter, right here for this metric, and RT is called the scaling factor, which is a function of time. And the idea is, what this scale factor means is that if you increase the scale factor with the time, so that means you are in an expanding universe, right? So you can see that this scaling factor in this Robertson-Walker metric is basically to look at the expansion or the contraction of the universe. So if it is increasing with the time, which means you are in an expanding universe, right? So this is why using, once you plug the Robertson-Walker metric, not the Robertson-Walker metric, actually connection coefficients, and then these appropriate tensors into the field equation with energy momentum tensor, you can solve it and look at how these K and RT parameters behave, right? So that's what we are going to look at throughout this chapter until the end. Right, so yes, that I have mentioned here, trying to find KRT, that is the expansion or the scaling factor, is a major preoccupation of cosmologists, as they play a key role in to understand the model of the universe, right? Because, so what we are trying to do is trying to find these K and RT values. And of course, the R naught is the current value of this scaling factor right now, and then how it changes with the time, and also this the curvature parameter K. And if you know all these three values, that will help a lot to understand the model of the universe, right? So that's what we are going to understand, and we'll discuss in these coming sections, right? Now let's move into this curvature parameter. And according to the cosmological principle that we now know, if the space is curved, then it must be constantly curved, right, at any point. So what that means is, we know that our universe is homogeneous and isotropic. And if that is the case, according to that principle, if the space is curved, then it must be constantly curved at every point, which means if it is curved, you should have the same curvature at each and every point, right? You know that we are in a homogeneous and isotropic universe, so that is the reason. And if you consider that fact, there are three types of constant curvatures that we can consider. So the number one thing is, according to the cosmological principle, if our space is curved, then it must be constantly curved. Then there are only three possibilities that we can have for the constant curvatures. Number one, it can be positively curved space, or it can be a closed surface, or it can be a negatively curved space, right? So those are the three possibilities that we could have. So which means, for our value of the curvature parameter, that is K, so the K can have three possibilities, right? So this curvature parameter is described by the spatial coordinates of the Robertson-Walker metric and determined by the curvature parameter K. And by rescaling R and R, K can take the following values. So these are the values. So these are the values that K can have. If K equals 0, it will be a flat universe. If K equals +1, it should be a positively curved one. k equal -1, it will be a negatively curved universe, right? Now you can look at what flat universe means, what a positively curved universe means, what is a negatively curved universe means, right? Now, if you look at flat space, so that is the normal, space that we know. If you draw a triangle in a flat space, then you know that all these three angles, if you add up, it will be 180 degrees. But it will not be 180. If it is a positively curved space, it should be greater than 180. If it is a negatively curved space, it should be less than 180. And I guess actually I was to put a small diagram, 3 diagrams here just to understand this thing. So I will put that before I upload. When I upload the new version of this. Right. Now that's some of the information that we have to learn about this Robertson-Walker metric. And some of the components of that, especially this curvature parameter and the scaling parameter. And I hope you now have a good idea about number one, about the cosmological principle. And I think I have convinced you that there are evidences to tell that the cosmological principle is correct. And then we talked about the expansion of the universe based on the Hubble law. We discussed what and how what actually this expansion means, and we newly learned about the cosmological redshift. And then we came into this section about how to mathematically explain this homogeneous and isotropic universe. And to satisfy that, we have defined got to know about the Robertson-Walker metric, and what we have doing up to now, we discuss different terms and different terms that appeared in the Robertson-Walker metric, especially about the scaling parameter and the curvature parameter, right? So it is important that we know all this information before we move on to talk about something called proper distance, and then about the Friedmann equations. Friedmann equations are basically, once you know the Robertson-Walker metric, you calculate connection coefficients and then the Riemann and Ricci curvature tensor, and then plug the energy momentum tensor into the right hand side, and then solve it for get these Friedmann equations, which we can use to discuss about the different models of the universe, right? So that's what we will be doing in these few days. Right, so I think this is a good point to stop today. As you know, the things are here. I don't want to spend hours talking about this thing. As you make sure that you go through this note, this is already uploaded to the LMS, and try to understand this at least, right? Anybody have any questions up to here?